This video is a summary of what's in Chapter 1 from the Math 2101 book. Now, if you're not studying this book, this could still be useful to you. But for students who are studying this book, you need to understand everything that I'm about to talk about. If you don't, it might mean that you need to spend a bit more time in Chapter 1. First thing I'm going to talk about is this situation. From home, I take a bus 4 kilometers to the metro station. Then I take the metro 6 kilometers to another metro station, and I walk the rest of the way to school, which is 1 kilometer. So this is a straightforward situation, but we're going to deal with it in a way that uses algebra. First, I'm going to make an equation that allows us to calculate the total distance using some variables. I'm not going to plug the numbers in yet. So let's use d sub t as total distance. And we'll say that that is equal to d sub b, which is the distance on the bus, plus d sub m, which is the distance on the metro, plus d sub w, which is the distance walking. Now, of course, this only makes sense if I define the variables. So I'm going to do so. Now, a lot of students see this type of variable and they don't like it. They don't like seeing all these little subscripts. It just looks confusing. But of course, it looks confusing when you don't know what each of the variables means. Once you do know what they mean, it's not very confusing at all. It's actually really well organized. But it's not the only way of making an equation. So what if I decide that x is my total distance, and a is the distance on the bus, b is the distance on the metro, c is the distance walking? Well, this also works. This works just as well, and a lot of students will find this a little easier to read and they prefer this method, but you still have to define your variables. So now we've covered the concept of using variables to represent different things in an equation. We're defining our variables and we're making our equation. And we can use this equation to calculate things. Let's try it. For this situation, the bus distance is 4, the metro distance is 6, and the walking distance is 1. So I can replace the variables with the numbers that go with them. d sub t, therefore, is equal to 4 plus 6 plus 1, and that means 11 kilometers is the total distance. Another way of doing it, though, is we don't always solve for the total distance. It might work in a way where we know the total distance, but we don't know one of the others. So what if we know the total distance is 11? And this time I'll use the ABC version of the equation. X is equal to 11. And let's say I don't know the bus distance. So the bus distance stays as A. The metro distance is still 6. The walking distance is still 1. I can still solve. My unknown is the A this time. So what I have to do is a little bit of algebra where I'm going to move the 6 and the 1 to the other side of the equals where they both become negative. And 11 minus 6 minus 1 is 4. The bus distance, therefore, is 4 kilometers. We knew that would happen. We knew the answer before we started. So you can see another thing that we have to be able to do. We have to be able to take an equation with variables, and it should not matter which of the variables is the unknown that we're solving for. Any of them we can solve for. Let's look at some other scenarios. What if, I'll erase some of this here. What if there's more than one way for me to get to school? What if, using the orange chalk, I can take a bus over here and it's 9 kilometers, and then I take a metro line that curves around this way and gets to the same metro stop, but by a different route. And let's say that's 14 kilometers. But I still end up walking 1 kilometer to school. We can illustrate a couple of things with this. Our total distance is going to be equal to the bus plus the metro plus the walk again. But this time, it's equal to 9 plus 14 plus the same old one that we already had. And that means the total distance is going to be 24 kilometers. So this equation was flexible. We could apply it to more than one scenario within these similar situations. That's interesting. Another thing that's interesting here is that we can see that either way, I have to walk 1 kilometer. Let's say I want it that way. Let's say I want the exercise of walking 1 kilometer the last kilometer before school. So no matter what way I manage to get to school, I always arrange to walk 1 kilometer at the end. This introduces the idea of a constant term. Our equation can be distance total equals distance bus plus distance metro plus 1. We don't need to have a variable because it's not varying, it's not changing, it's always 1 within this situation that I'm describing. So this is what's called a constant term. A constant term is when you have a number that's in your equation and it's not a variable that can be changed to be various different values. It's always going to be that amount. Well, in that case, you don't have to put a variable. You can put the number in. You have used a constant term. Here's another scenario. We'll go back to the original one. But I'm going to keep my 1. I have my constant term in my equation now. I'm going to erase this alternate route, which looked like it was a bit of a waste of time anyway, and we'll go back to our original way of getting to school: bus 4 kilometers, metro 6 kilometers, walk 1 kilometer. But what if I got on the bus and I got all the way to the metro stop and then I realized I forgot my homework? I get back on the bus and I go all the way back home and I pick up the homework, and then I get back on the bus and I go all the way to the metro station again. So it's the same route to get to school as usual, except that I tripled the bus distance by riding the bus 3 times. So how can we express this? The distance total can be equal to 3 times the distance bus plus the distance metro plus the 1 kilometer I always walk. So we have our constant term. We still have our variables, but this time the distance on the bus is being tripled. I have just created a numerical coefficient for this variable. If I go back to my other way of showing the equation, x equals a plus b plus c, I'll say x is equal to 3a plus b and plus 1. So I'm using my constant term, and I have a numerical coefficient. This is a little hard to look at. This I find is a little easier to look at. I think most students would prefer this. But what you see is that in order to solve the total distance problem, we have to multiply the bus distance by 3. So let's do it. X is equal to 3 times the 4 kilometers plus the 6 kilometers plus the 1 kilometer, which is 12 plus 6 plus 1, which is 19 kilometers. So if I forget my homework and I have to ride the bus 3 times, I go 19 kilometers instead of the usual 11. The numerical coefficient is very useful when we're building an equation like this. Let's try another scenario though. How about, and I'll go back, I'll keep the ABC approach here. How about we triple all the distances? The distance total is our x. X is equal to a plus b plus 1. But let's say, I don't know, I'm really early and I want to kill some time, and I ride the bus 3 times on purpose, and then I ride the metro 3 times on purpose, and then I walk 3 kilometers instead of 1 kilometer. Well, basically I'm multiplying each of these distances by 3. So x is equal to 3a plus 3b plus 3 times 1, which is 3 times 4 plus 3 times 6 plus 3 times 1. which is 12 plus 18 plus 3, which is 33 kilometers. Well, I knew that my original distance was 11 kilometers, so I'm not too surprised to see that if I multiply all of the smaller distances by 3, I end up with triple 11, 33 kilometers is that total distance. And this is a way of looking at this where we're taking advantage of the numerical coefficients, but it's not the only way to look at it. We can also say x is going to be equal to 3 times the usual. 3 times bracket a plus b plus 1. We can fill in our a and our b. We still have the constant 1. We'll keep it as 1, but we can fill in our a and our b with the 4 and the 6. And we can say, oh, well, bedmass, I'm going to do the bracket before I multiply. So it's 3 times 4 plus 6 plus 1, which is 11, which is 33. I knew that would happen. But that's not the only way we can show this. We can say x equals 3 times 4 plus 6 plus 1. We can multiply the 3 by the 4, multiply the 3 by the 6, multiply the 3 by the 1. We can do it that way instead if we want. 3 times 4 is 12, 3 times 6 is 18, 3 times 1 is 3. We get the same answer. What we're dealing with here is the way we multiply across a bracket. We're combining addition and multiplication in an interesting way, and it's a type of manipulation in algebra that students have to do a lot. So it's a good thing to practice, and it's a good thing to understand. How about a verification? Let's do a verification now. I'll take this answer and I'll plug it in. 33 should be equal to, I'm using this version of the equation right now. 33 should be equal to 3 times 4 plus 6 plus 1. It's not very different from what I was already doing, except that I know the answer. So I've calculated the answer and I want to verify it. Verification involves taking advantage of something that's true about equations. Equations have to be equal. The two sides have to be equal. That's why we call them equations. Equals, equation. So what's on the right side should be equal to what's on the left side. And that is an important principle in our understanding of algebra, because I can use it in a lot of different ways, and one of them is I'm going to use it for my verification right now. 33 has to be equal to 3 times 11, and yeah, 3 times 11 is 33. I end up with 33 equals 33. This is a way of checking my answer to see if it's right. Very useful. It's not the only useful thing we can do with this. Another thing that we can do when we know that the left side of an equation is equal to the right side is we can write it backwards. We can say, oh, 3 times 4 plus 6 plus 1 is equal to 33. It's the same thing that I wrote up here, but this time I have the 33 on the right side and this multiplication with the bracket on the left, and it doesn't matter. Because, again, what's on the left side is equal to what's on the right side. So it doesn't matter if you write your equation forwards or backwards. Either way, it's an equation, and the two sides are equal. Let's talk a little bit about algebra. Basic algebra skills involve being able to deal with the 4 operations: addition, subtraction, multiplication, and division. When you're in an algebra situation, in an expression or in an equation, we're in an equation right now. So let's create some examples. I'm going to leave my bus, metro, walk example for now and go into some more straightforward small examples. X plus 4 equals 12. We want to know what x is. This is a basic little algebra problem. We take advantage of something that involves the left side being equal to the right side of the equation, which is they're equal. And they have to stay equal, or else we don't have an equation. We're breaking our rules. The rule of algebra is the left side. Whatever we do on the left side, we should also do on the right side. So if I want to simplify this, I'd like to get rid of that 4. The 4 is being added to my x, and I don't want it there. I want my x alone. The goal of algebra is to have your variable alone on one side of the equals. So how do I get rid of a 4 that's being added? I do the opposite of addition, which is subtraction. So x plus 4 minus 4. I'm going to subtract a 4 so that these will cancel. and then my x will be alone. But I can't subtract a 4 over here unless I subtract a 4 over there. The plus 4 minus 4 cancels, x is isolated and is equal to 12 minus 4, which is 8. We have a correct answer. That was a very useful thing to do. A lot of students will very quickly start using the shortcut, which is to just say, I'm getting my x alone by moving the 4 to the other side where it becomes negative. That is really what happens. So if you're not making mistakes, it's okay to take this little shortcut and you still get your correct answer. But this is what we're really doing. What we're really doing when we do that thing where we move the 4 to the other side and it becomes negative is we are taking advantage of this rule where we're allowed to subtract a 4 from both sides. We're allowed to do anything to one side so long as we do the same anything to the other side. Let's say that was addition because the 4 was being added to the x. How about subtraction? X minus 5 equals 10. I'm subtracting a 5. I want to get rid of it. So I'll get rid of it by adding a 5 to both sides. Doing it on both sides means it's okay. These cancel, x is isolated, and my answer is 15. I have a correct answer. Again, I can write x minus 5 equals 10. X equals 10 plus 5. I'm doing the shortcut. I'm not showing this part. But I have to know that minus 5 becomes a plus 5. So with addition and subtraction, when you decide you're moving a number to the other side of the equals, it changes sign. And if you know that, you won't make mistakes. And you'll be able to do it correctly with or without the shortcut. What about division and multiplication, though? If my x is being multiplied by a 6, and I want to get rid of that 6, I have to do the opposite. The opposite of addition was subtraction. The opposite of subtraction is addition. The opposite of multiplication is division. I'm going to divide it, the 6x, by a 6 so that I can cancel, but I have to divide both sides by a 6. These cancel. X is equal to 30 divided by 6, which is 5. The shortcut still exists. 6x equals 30. The shortcut is x must be equal to 30 divided by 6, which is 5. It works, but notice how it didn't change signs. I was dividing both sides by a 6. That 6 that seems to disappear from the left side and go over to the right side did not become negative, because that happens when you're doing addition and subtraction algebras. But when you're doing multiplication and division algebras, that doesn't happen. So let's do the last one, which is the division. X over 2 equals 21. I'm dividing my x by a 2. I want to do the opposite so that I can cancel the 2. The opposite of dividing is multiplying, so I'm multiplying the left side by a 2. But I have to multiply the right side by a 2 as well. These cancel. X is isolated and is equal to 42. The answer to 21 times 2, I have my answer. Shortcut. X is equal to 21 times 2. I'm not showing this part. I'm doing the shortcut. I'm getting the right answer. And the 2 didn't change signs. Addition and subtraction, the number that moves across the equals changes signs. Multiplication and division, it doesn't. That is the basic algebra skills as they apply to the 4 operations: addition, subtraction, multiplication, and division. We have covered all of the concepts that are taught in Chapter 1 of the Math 2101 book. You need to practice all of these little tricks enough so that you're going to remember them. Because not only do you need them for the rest of this book, not only do you need them for the final exam that you'll do at the end of this book, but you're always going to need all of these concepts for every bit of math you do from now on. These are not very difficult concepts, but they're important concepts because the basics of algebra get used in all of the type of math that's ever taught after you learn algebra. It's crucial that you understand these skills. So I hope if you're not taking the Math 2101 book, that what I've discussed helps you. But if you are taking the Math 2101 book, it's crucial that you understand all the concepts that are put forward in this video, because if you don't, it means you need to get back into Chapter 1 and practice a little bit more so that you can remember this stuff. It's important.